A ghostly ring of light expands silently in the depths of space, a message from a star that died centuries ago. This is a light echo, a celestial phenomenon where ancient light from violent explosions bounces off cosmic dust and finally reaches us, creating luminous apparitions across the galaxy. By the end of this journey, you will understand how these echoes act as a cosmic time machine, letting us witness the universe's most dramatic events long after they have faded from view. We will uncover how a single flash can be replayed multiple times and what these delayed signals reveal about the secret lives of black holes. What part of the universe's hidden history would you most want to witness for yourself? That initial flash of a dying star is only the beginning of its story. Long after the main blast fades from view, a second, more subtle performance can unfold. Imagine a supernova whose light traveled for centuries to reach Earth. Then, years or even decades later, astronomers witness new rings of light appearing in the sky, emanating from that very same spot. This is not a new explosion. It is a light echo, a ghostly replay of the original cataclysm. The mechanism is as beautiful as it is simple. The first pulse of light from the stellar death races outward in all directions. Most of it comes straight to our telescopes, but some of that light travels on a different path, striking vast, dark clouds of interstellar dust. These cosmic dust bunnies, floating light years away, act like a giant celestial mirror. They catch the ancient light and reflect it toward us, delivering a message that took the long way home. This creates the illusion of an expanding ring of light, a shimmering phantom growing slowly across the heavens. It is the astronomical equivalent of hearing an echo in a canyon, where your shout travels to a distant cliff face and bounces back to you. Only here, the canyon is light years across, and the shout is the death cry of a son. The first time this was clearly seen was with Supernova 1987A. The initial blast was spectacular, but the real surprise came years later when perfect, glowing rings materialized around the remnant. They were not part of the explosion itself, but its reflection, a delayed broadcast from the past. This phenomenon gives astronomers an incredible power, the chance to study a single cosmic event multiple times. We get to observe the same flash of light from different angles and at different moments, all from one original source. The existence of an echo depends entirely on the geometry of space. Is there a dust cloud in just the right position to catch the light and beam it our way? This transient nature makes each one a precious and fleeting gift. To truly understand these echoes is to grasp how light, the universe's ultimate messenger, travels and interacts with the silent, dusty scaffolding between the stars. So how do we actually find these cosmic mirages? The speed of light is the universe's ultimate constant, a cosmic speed limit that nothing can break, yet its journey is rarely a straight line. When that initial, violent flash from a supernova erupts into the void, it races outward as a perfect, ever-expanding sphere of energy. Most of this light travels directly toward any observer in its path. But a small fraction of this brilliant sphere encounters something in its way, a vast, dark cloud of interstellar dust. These are not solid walls, but diffuse collections of tiny particles, each one a potential cosmic mirror. When a photon, a single particle of light, slams into one of these dust grains, it does not simply stop. It scatters, bouncing off in a new direction like a billiard ball. Some of these scattered photons, by pure chance, are now aimed directly at Earth. They arrive years, even decades, after the light that came straight to us, delivering a delayed, fainter copy of the original event. This is the heart of a light echo, a slower, reflected version of a flash from the past. The shape we see in the sky, that ghostly ring, is a direct result of geometry. Think of the dust cloud not as a flat sheet, but as a vast, hollow shell with a dead star at its center. The light from the explosion expands, finally striking the inner surface of this cosmic shell. From our vantage point on Earth, we see only the part of the shell that is precisely aligned to reflect light into our eyes. This alignment creates the illusion of a ring, and as the sphere of light continues to expand through space, it illuminates progressively more distant parts of the dust shell. This makes the ring appear to grow larger in our sky over the years, a phantom swelling with time. The genius of Albert Einstein's theories helps us map these paths, showing how the fabric of spacetime itself can be curved by gravity, subtly bending the trajectory of light on its long journey. At the smallest scale, the rules of quantum electrodynamics govern the precise dance between a single photon and a dust grain, a fundamental interaction that makes the entire cosmic echo possible. These abstract principles are no longer just equations on a page. They are transformed into observable, tangible rings of light in images from the world's most powerful telescopes. The physics provides the script for this celestial play, but to see the performance, astronomers need the right tools. How do we actually capture these faint, ghostly signals from across the galaxy? Centuries before we had a name for them, light echoes were already being recorded. In 1572, the famed astronomer Tycho witnessed a brilliant new star flare into existence in the constellation Cassiopeia, a star so bright it was visible even in the daytime sky. This was a supernova, the violent death of a star, and though its visible light faded over the following year, its story was far from over. Tycho meticulously documented what he saw, unknowingly creating a timestamp for an event whose light was still traveling through the cosmos, destined to bounce off unseen dust clouds and return as an echo. Modern astronomers, using powerful telescopes, would later detect the expanding remnant of that very explosion, the ghost of Tycho's star. But the first true, recognized glimpse of a light echo came over 3 centuries later with Nova Persei in 1901. After the nova's initial flash faded, astronomers were astonished to see a faint ring of light slowly expanding around its location. They theorized it was light from the original eruption, reflected off a cloud of interstellar dust, finally arriving at Earth months later. Without the technology to study it in detail, the phenomenon remained a curious puzzle. The real breakthrough arrived in the 1980s with Supernova 1987A. Advanced cameras on the Hubble Space Telescope captured multiple, perfect rings of light blossoming around the supernova years after the initial blast, confirming beyond any doubt that we were seeing reflected light from the past. This transformed light echoes from a theoretical oddity into a standard astronomical tool. Looking back, we now realize that historical records of transient brightenings near known supernova remnants might have been early, unrecognized sightings of these very echoes. Our ancestors saw the ghosts in the sky, but they lacked the means to understand the message they carried. This long history makes our current ability to not only see but also analyze these echoes all the more profound. So how does modern astronomy actually capture and decipher these faint cosmic whispers? Finding these faint cosmic ghosts requires a special kind of hunt, one that spans years and relies on the most patient eyes we have. Our greatest tool in this search is time itself. Astronomers practice time domain astronomy, which simply means they take picture after picture of the same patch of sky, night after night, year after year. They are looking for the subtlest of changes, a faint ring that was not there before, or one that has grown imperceptibly larger. Space telescopes like Hubble and Spitzer are masters of this craft. Positioned above our shimmering atmosphere, they use incredibly sensitive cameras to monitor these faint glows, tracking their slow expansion with unwavering precision. They capture the delicate rings in stunning detail, transforming a theoretical concept into a visible, measurable reality. Yet the sky is vast, and even Hubble cannot watch everywhere at once. This is where giant ground-based observatories come in. Their wide-field surveys act like a panoramic security camera for the entire sky, constantly scanning for any new flicker of light, any transient event that might signal the birth of a new echo. But simply seeing a ring is not enough. We need to understand its message. That is where spectroscopy performs its magic. By breaking down the echo's faint light into a rainbow of colors, astronomers can read its unique fingerprint. They can determine the chemical composition of the original explosion and even measure the immense velocity of the expanding debris, all from a reflection that arrived centuries late. The final, crucial step happens not at the telescope, but inside powerful computers. Advanced algorithms sift through mountains of image data, distinguishing the true, faint signal of a light echo from the background glare of the galaxy. They turn what looks like random noise into structured, reliable scientific data. This entire technological symphony allows us to collect these cosmic whispers and amplify them into a clear story. And the first story these echoes have told us, the most dramatic one, is the final, violent act in the life of a star. These cosmic ghosts deliver their most profound messages from the violent graves of supernova. A star's death is a chaotic, messy affair, and light echoes give us a front-row seat to the autopsy, revealing details the initial blast often hides. The echoes from Cassiopeia A, the remnant of Tycho's supernova, told a surprising story. By studying the faint, reflected light, astronomers realized the explosion was not a perfect sphere. It was lopsided, a catastrophic detonation that blasted jets of stellar material out into space in wildly uneven directions. This asymmetry is a crucial clue, helping us piece together the final, frantic moments inside a collapsing star. The true power of an echo, however, lies in its light signature. When astronomers pass that faint glow through a spectrograph, splitting it into a rainbow of colors, they can read the chemical fingerprints of the explosion itself. They see the distinct signatures of iron, silicon, and oxygen forged in the star's final inferno, and then blasted across space. This directly confirms our theories of nucleosynthesis, the cosmic process where stars create the very elements that make up our world and our bodies. The iron in your blood was once manufactured in a cataclysm like this. Beyond chemistry, these echoes act as cosmic measuring tapes. Because we know the speed of light is constant, the precise timing and geometry of an echo's expansion allow us to calculate the distance to the supernova independently, cross-checking and refining the vast scales of our universe. Perhaps most intriguingly, some complex echoes suggest that what we record as a single historical supernova might actually be the blended light of multiple stellar explosions, occurring close together in time and space from our distant viewpoint. Each faint ring is more than a memory, it is a fossilized moment of stellar death, preserving the physical conditions of that instant for centuries. This narrative of cosmic violence, however, is not limited to the death of stars. But the stellar ghosts are not the only voices echoing in the dark. A more profound and terrifying presence also leaves its mark. Black holes, those infamous cosmic vacuums, are not always silent. When a star or a gas cloud drifts too close, the black hole's immense gravity shreds it apart, pulling the material into a swirling, superheated disk. This process is not a quiet consumption. It is a violent eruption, a flash of intense X-rays and gamma rays that can outshine an entire galaxy for a brief, brilliant moment. And just like a supernova's light, this flash can bounce off nearby clouds, creating an echo of its own. Our own Milky Way galaxy houses a perfect example. At its heart sits Sagittarius, a star, a supermassive black hole that is currently quiet. But by studying the X-ray light echoing from giant molecular clouds near the galactic center, astronomers have made a startling discovery. These faint, reflected signals are the ghosts of immense flares, outbursts that occurred not decades but centuries ago. We are essentially reading the diary of a sleeping giant, learning about its past feeding frenzies long after the meal was finished. The echoes provide a timeline. By mapping which clouds are lit up and calculating the light travel time, scientists can reconstruct a history of the black hole's activity. A cloud farther away might show an echo from a flare 500 years ago, while a closer one reveals a more recent outburst from 300 years past. This data is challenging everything we thought we knew about black hole behavior. It suggests that periods of supposed dormancy are often punctuated by these violent eruptions, forcing us to rethink their activity cycles. The implications stretch far beyond our own galaxy. In distant galaxies, the brilliant cores known as quasars are powered by supermassive black holes in a near-constant state of feasting. Light echoes from these quasars, often seen as vast, luminous light echoes or ionization echoes in surrounding gas, reveal how these cosmic engines influence their entire galactic environment, shaping the birth and death of stars across thousands of light years. Understanding these echoes is more than just historical record-keeping. It is a key to prediction. By learning the rhythms of a black hole's hunger from its past echoes, we gain clues about when it might awaken again. This entire journey from stellar deaths to black hole eruptions relies on our ability to measure the cosmos with precision, and it turns out these same light echoes provide one of the most elegant cosmic measuring tapes we have ever found. There is a profound elegance in how these cosmic mirages become universal measuring tapes. A light echo's expanding ring is not just a beautiful illusion, it is a precise geometric figure drawn across the void. Astronomers can measure the time it takes for the ring to grow by a certain amount, and since they know the speed of light is a constant, this timing reveals the true physical scale of the echo. It is a celestial form of triangulation, using the dust cloud as a fixed point in space. The concept is similar to parallax, the way your finger seems to shift position when you view it with one eye closed and then the other. But instead of using two viewpoints from Earth's orbit, this method uses the echo's own expansion over time, with the dust cloud acting as a giant, passive reflector. This technique was brilliantly demonstrated with the strange star V838 Monocerotis. This object underwent a mysterious outburst, not a classic supernova, but something that enveloped it in a colossal shell of gas. As light from that outburst traveled outward, it illuminated vast, pre-existing dust shells around the star, creating a spectacular series of light echoes that expanded for years. By meticulously tracking this expansion with the Hubble Space Telescope, astronomers could calculate a direct geometric distance to the star itself. This provided a crucial, independent measurement that helped calibrate other steps on the cosmic distance ladder. That ladder is our system for measuring the universe, where each rung relies on the one below it. A small error at a nearby rung can become a massive miscalculation for the most distant galaxies. Light echoes offer a unique advantage because they do not depend on an object's intrinsic brightness. Most cosmic distance markers, like Cepheid variable stars or Type 1a supernova, are known as standard candles. They work because we believe we know their true brightness, and by measuring how dim they appear from Earth, we can calculate their distance. But what if our assumption about their true brightness is slightly wrong? A light echo bypasses this problem entirely. It provides a purely geometric distance, a measurement based only on the laws of physics and the speed of light. This makes it an invaluable independent check, especially for historical supernova whose original explosions were seen centuries ago, long before modern measurement techniques existed. By applying this echo method to the remnants of these ancient stellar cataclysms, we can finally pin down their precise locations in our galactic neighborhood, refining our three-dimensional map of the Milky Way. And every accurate distance we add to that map helps us better understand the rate at which the entire universe is expanding. Yet to trust these measurements completely, we must understand the very substance that makes them possible, the cosmic dust that writes these shimmering messages across the sky. These silent dust clouds are far more than simple cosmic mirrors. The faint light that bounces back to us carries a hidden fingerprint, a detailed chemical signature of the very dust grains it touched. When astronomers dissect the spectrum of a light echo, they are not just studying the original star, they are conducting a remote chemical analysis of an interstellar cloud light years away. The light we receive is subtly altered by its encounter with the dust. Specific wavelengths are absorbed, creating dark lines in the rainbow of colors that reveal the presence of minerals like silicates, the building blocks of rocky planets, graphite, a form of carbon, and even thin layers of water ice coating the grains. Each echo becomes a probe, illuminating the invisible material that drifts in the vast emptiness between stars. A stunning example comes from the volatile system Eta Carinae, a massive star on the brink of destruction. Light echoes from its past eruptions revealed an unexpected abundance of carbon-rich dust grains. This suggests that the violent stellar winds in that region create a very specific chemical environment, one that favors the formation of carbon compounds over other elements. It is like analyzing a single grain of sand and learning the entire geological history of the beach it came from. But the secrets do not stop with chemistry. The light itself can become polarized as it scatters off the dust, meaning its waves vibrate in a preferred direction. This polarization is a direct clue to the physical arrangement of the dust grains. It tells us that these microscopic particles are not randomly oriented. Instead, they are aligned like countless tiny compass needles by the weak but pervasive magnetic fields that thread through the galaxy. This alignment gives us a way to map these invisible magnetic forces, tracing their influence across interstellar space. All of this data helps scientists model the entire life cycle of cosmic dust. We can track how these grains condense in the cool, outflowing winds of aging stars, how they drift for millions of years, and how they are eventually destroyed by the shockwaves from the very supernova that create their most beautiful echoes. This cycle is fundamental to the cosmos. Without dust, there would be no dense clouds to collapse and form new stars and planetary systems. The very stuff of worlds is forged and recycled in this endless loop. So the next time you see an image of a glowing light echo, remember you are not just looking at a ghost from the past. You are looking at a detailed map of the universe's hidden scaffolding, a blueprint of the raw materials from which everything, including us, is made. The perfect sphere is a comforting idea, but the universe rarely deals in such simple shapes. Light echoes have torn apart that symmetrical ideal, revealing that stellar explosions are chaotic, messy, and profoundly lopsided events. Look closely at the echoes from supernova 1987A. Instead of a uniform ring of light, astronomers observed distinct, brighter spots within the glowing circles. These were not flaws in the mirror. They were spotlights illuminating dense clumps of material, massive chunks of the star that were violently ejected in one direction while other parts of the star flew off in another. It was the signature of a turbulent, fragmented collapse, a far cry from the neat, expanding bubble we often imagine. Sometimes the evidence of asymmetry is even more direct. An echo might manifest not as a complete ring, but as a broken arc or a faint, shimmering crescent. This tells us one of two things. Either the dust cloud itself is patchy, leaving gaps in the reflection, or the explosion's own light was intensely directional, a focused beam that only illuminated a specific segment of the surrounding dust. This has a direct consequence for the entire cosmic ecosystem. When a star dies asymmetrically, it does not scatter its newly forged elements evenly into the void. Precious metals like iron and gold, the very materials for future planets and perhaps even life, are sprayed into specific regions of space, creating enriched pockets and leaving others barren. This uneven distribution directly influences the chemical makeup of the next generation of stars and the planetary systems that form around them. To decipher this chaos, astronomers have become cosmic cartographers. By meticulously mapping how the shape and brightness of a light echo change over months and years, they can reconstruct the full three-dimensional geometry of the explosion long after the fireball has faded. It is a form of celestial tomography, building a slice-by-slice model of a single cataclysmic moment frozen in time. This three-dimensional view provides the crucial clues needed to understand the engine of the explosion itself. Was it the star's rapid rotation that flung material outward from its equator? Did powerful magnetic fields channel the blast into polar jets? The asymmetries revealed by the echoes feed directly into supercomputer simulations, forcing theorists to refine their models of these ultimate stellar deaths. With the three-dimensional structure of these explosions now coming into focus, a deeper question emerges. What were these stars like in the moments just before they died? The final moments before a star explodes are shrouded in secrecy, but its ghostly echo can betray its identity. For historical supernova like the one Tycho saw, astronomers search for a faint, reflected glimmer of the progenitor star itself, the specific sun that met its violent end. This is like finding a person's photograph in a mirror long after they have left the room. If successful, the color and intensity of that ancient, bounced-back light can reveal whether the star was a red supergiant, a white dwarf, or some other type, finally putting a name to the celestial victim. In more recent explosions, light echoes act as delayed probes, illuminating the environment around the star just before it died. They can reveal the presence of a previously hidden binary companion, a second star whose gravitational pull may have triggered the cataclysm. Echoes can even map out the structure of dense stellar winds that the star was shedding in its final, unstable years, winds that the supernova blast wave later plowed into. This environmental evidence is critical for classifying the supernova and understanding its trigger mechanism. Was it the merger of two white dwarfs pushing over a critical mass limit, or the catastrophic core collapse of a single, massive star? Each scenario leaves a different fingerprint on the surrounding space, and the echo captures that fingerprint. The most direct confirmation comes from a cosmic game of spot the difference. By analyzing the light from an echo and then scouring decades-old archival images of that same patch of sky, astronomers can sometimes pinpoint the exact star that is now missing. It just vanished, its location now occupied by a glowing remnant. This turns every light echo into a unique time capsule, preserving a snapshot of a stellar system that was utterly obliterated, information that the initial flash of the explosion itself often destroys or obscures. Identifying these progenitor stars is not merely an exercise in cosmic history. it is fundamental to forecasting future explosions within our own galaxy. By understanding which types of stars explode and under what conditions, we can better predict the fate of brilliant, unstable giants like Betelgeuse. This search for stellar origins, however, relies entirely on the intricate tapestry of material that floats between the stars, the very medium that writes these shimmering messages across the sky. These faint echoes do more than replay history, they illuminate the invisible architecture of space itself. The vast expanse between stars is not a perfect vacuum. It is filled with a diffuse and complex mixture known as the interstellar medium, a cosmic fog of gas and dust that usually remains hidden in shadow. A light echo acts as a perfect flashbulb, firing a single, brilliant pulse that travels for years before striking this cosmic haze. As the echo expands, it lights up successive layers of this material, revealing their precise distances, their densities, and their intricate shapes. The echoes from V838 Monocerotis provided a textbook example. Instead of a single ring, astronomers observed multiple, concentric rings of light blossoming over time. Each ring was not a new event, but the same flash of light illuminating a different, distinct sheet of interstellar dust floating between the star and our telescopes. It was like watching a single camera flash go off in a vast, dark cathedral, successively revealing one ornate pillar, then a distant archway, then a far wall, each at a different distance from the camera. This process allows scientists to construct a detailed three-dimensional map of the interstellar medium. We can see not just flat images, but the true depth of space. These maps reveal colossal cavities blown clean by ancient stellar winds, delicate filaments of gas twisted by unseen forces, and the sharp edges of dark molecular clouds where new stars are likely forming. This dynamic view is crucial. A static image of a cloud tells you it is there, but watching how a light echo brightens and fades as it sweeps across that cloud reveals its internal turbulence, how its material clumps and swirls. The way the light scatters and becomes polarized even traces the faint magnetic fields that run through these clouds, guiding the flow of matter on a galactic scale. Understanding this structure is fundamental to the life cycle of a galaxy. The interstellar medium is the raw material for everything, the reservoir from which stars are born and the repository where their ashes are returned. By mapping its three-dimensional form with these echoes, we learn how galaxies recycle their material, how efficiently they form new stars, and how energy from stellar explosions propagates through this tenuous medium, shaping its future. This ability to watch the interstellar medium react in real time, to see it respond to the shock and radiation of a cosmic event, naturally leads us to wonder about repeating outbursts. Some stellar outbursts are not final, but part of a repeating cycle of cosmic violence. In the constellation Ophiuchus, a star named Oris Ophiuchi performs a deadly dance with a red giant companion. The dense white dwarf siphons material from its bloated neighbor until the stolen gas on its surface reaches a critical pressure, igniting a thermonuclear firestorm that we see as a brilliant nova. This is not a one-time event. It erupts roughly every 15 to 20 years, and each blast sends a new pulse of light racing outward. These recurring explosions create a layered history, with each new outburst generating its own set of light echoes that bounce off the expanding shells of debris from all the previous eruptions. We are not looking at a single ghost, but at an entire spectral archive. By comparing the echoes from the 1985 eruption to those from 2006, astronomers witnessed the evolution of the system in real time. The newer echoes showed how the latest shockwave was plowing into the older, slower-moving material ejected decades before, heating it and reshaping the nebula. The surrounding dust and gas act as a celestial recording medium, preserving the intensity, direction, and chemical composition of each separate event. This layered chronicle reveals the white dwarf's accretion process in stunning detail, showing how efficiently it steals mass and how violently it expels the excess. Each eruption adds a tiny bit of mass to the white dwarf, pushing it closer to the ultimate tipping point, the Chandrasekhar limit, where it could be completely obliterated in a Type 1, a supernova. The echoes provide a direct measurement of the mass ejected in each cycle, critical data for forecasting which of these recurrent nova might be a future supernova in the making. This transforms the study of these systems from a snapshot into a long-term diary, documenting the slow, incremental steps toward a final, catastrophic detonation. This record of recurring stellar fury is written in light, and it may also hold the key to understanding another, even more enigmatic form of cosmic energy. The mystery of cosmic rays has haunted scientists for over a century. These are not rays of light, but invisible, high-energy atomic fragments racing through the galaxy at nearly the speed of light. They constantly bombard our planet, yet their exact origins have remained one of astronomy's greatest puzzles. Now, light echoes are providing a crucial clue, pointing directly to the cosmic accelerators responsible. The leading suspects have always been supernova remnants. When a star explodes, it creates a colossal shockwave that expands for thousands of years, plowing through the interstellar medium at supersonic speeds. These shock fronts are believed to be natural particle accelerators, far more powerful than anything we could build on Earth. Within the turbulent, magnetized chaos of these expanding shells, protons and electrons can be caught, whirled around by magnetic fields and flung outward with unimaginable energy. They become the cosmic rays that permeate our galaxy. The challenge has been proving this theory directly. We cannot see the particles themselves at their source. This is where light echoes become an indispensable proxy. By studying the faint, reflected light from a historical supernova, astronomers can map the precise structure and strength of the magnetic fields within those shockwaves. They look for subtle changes in the echo's brightness and polarization over time, which reveal how energy is being channeled and concentrated in the remnant. A stunning piece of evidence comes from the echoes of supernova 1006. Observations show that the regions of its remnant glowing with the highest energy gamma rays align perfectly with areas where light echoes revealed the most powerful shock fronts and intense magnetic fields. Gamma rays are the signature of cosmic ray activity, produced when those accelerated particles collide with other matter. This correlation is the smoking gun, confirming that these supernova remnants are actively accelerating particles, not just for years, but for centuries after the initial explosion. The echoes allow us to measure the efficiency of this process, showing how much of the explosion's raw energy is converted into the invisible rain of cosmic rays. This has profound implications far beyond the remnants themselves. These high-energy particles influence the very ecology of our galaxy. They help drive the chemical evolution of interstellar clouds, and when they strike planetary atmospheres, they can affect climate and even mutation rates in life. By using light echoes to understand these galactic accelerators, we gain a deeper appreciation for the invisible forces that have subtly shaped our own planet's history and the potential for life elsewhere in the cosmos. Seen through the lens of light echoes, a galaxy transforms into a single, vast, breathing ecosystem. Each supernova explosion is not an isolated death, but a forceful pulse of energy that ripples through the galactic environment, seeding the void with newly forged elements and turbulent shockwaves. It is a cycle of creation and destruction on an epic scale, and these ghostly reflections allow us to witness the individual moments that define it. In the Carinae Nebula, a colossal stellar nursery, light echoes are not just memories of singular blasts. They are chronicles of ongoing sculpting. The intense radiation and powerful winds from the nebula's most massive, short-lived stars carve out vast cavities in the surrounding gas, compressing other regions into dense knots that will one day collapse to form new solar systems. When one of these giants finally explodes, the light echo from that supernova captures the instant its shockwave slams into the very cloud it helped create. A wave of energy that can either trigger a new burst of star formation by compressing the gas further, or snuff out nascent stars by violently dispersing their stellar cribs. This delicate balance is known as feedback, the self-regulating mechanism that dictates a galaxy's growth and ultimate shape. A galaxy with strong, frequent feedback from massive stars will have its star-forming gas blown away, quenching further birth and leading to a quiet, elliptical maturity. A galaxy with weaker feedback may continue forming stars in a more disordered, spiral structure for billions of years. Light echoes provide the crucial time-lapse snapshots of this process in action. They show us the precise moment heavy elements like oxygen and iron, forged in the stellar furnace and blasted outward, are injected into the interstellar medium. We can literally watch the galaxy enriching itself, recycling the ashes of dead stars into the raw material for new worlds and potentially new life. This ecological perspective forces us to stop seeing stars as isolated points of light and to start viewing the galaxy as a single, interconnected entity, where every stellar death contributes to the potential for future birth. The same fundamental forces are at work in the vast gulfs between galaxies, where echoes carry tales from even more immense cosmic engines. Our own galaxy is just one stage in a cosmic theater playing out the same dramas everywhere. The faint whispers of light echoes travel to us from other galaxies, carrying stories that help us see the universe in a whole new light. When we observe a supernova in a nearby galaxy like the Large Magellanic Cloud, we get a remarkably clean view. Supernova 1987 was a perfect example. Because this galaxy is a companion to our own, its light has to travel through far less of the Milky Way's obscuring dust to reach us. It is like listening to a concert from a seat in a quiet, acoustically perfect hall instead of a noisy, crowded street. The echoes we saw from that explosion were sharp and clear, providing an unparalleled laboratory to test our models of stellar death without our own galactic environment getting in the way. These phenomena reach across truly staggering distances. In galaxies millions of light years away, we can sometimes catch the faint, reflected glow from quasars, the intensely bright cores of galaxies powered by supermassive black holes. A quasar might flare brightly for a period, and years later, we see that same flash of light reflected off vast clouds of gas within its host galaxy. This echo reveals the intricate relationship between the black hole and its home, showing how these cosmic engines flood their galaxies with radiation, heating or blowing away the raw material for new stars and effectively regulating galactic growth. Similarly, a tidal disruption event where a star is shredded by a black hole's gravity can also create an echo. The reflected light shows us how the stellar debris swirls and falls into the abyss, a delayed broadcast of a distant cataclysm. These extra-galactic observations are the ultimate test for our theories. A model for how a star explodes is only robust if it works for supernova in the Andromeda Galaxy, as well as those in our own backyard. By comparing echoes across different galactic environments and across cosmic time, we can universalize our understanding of physics. They even provide a unique check on the expansion of the universe itself. When we measure the distance to a far-off galaxy using a light echo, We can compare it to the distance calculated from its redshift, the stretching of its light due to cosmic expansion. Any discrepancy forces us to re-examine our fundamental cosmological parameters, refining our knowledge of dark energy and the ultimate fate of everything. Capturing these faint signals from across the void is one of astronomy's greatest technical challenges. It requires pushing our telescopes to their absolute limits, developing ever more sensitive cameras and sophisticated software to tease a barely their ring of light from the background glow of an entire galaxy. The pursuit of these cosmic phantoms drives innovation, leading to the advanced instruments that will define the next generation of observatories. This grand, extra-galactic dimension proves that the principles we uncover locally are truly universal laws. And just as these echoes illuminate the deaths of stars, they can also be used to resurrect their origins, turning the sky into a dig site for stellar archaeology. The faint glow of a light echo is more than a memory, it is a fossil. Just as a paleontologist brushes dust from a Tyrannosaurus bone, an astronomer uses these cosmic reflections to excavate events from the deep past, a practice we call stellar archaeology. The sky is not a flat canvas, but a layered archive, with each ghostly ring representing a different stratum of galactic history. Some of these echoes come from supernova so ancient they exploded before the invention of the telescope, even before recorded human history. Their initial flash swept past Earth unseen, but their echo, traveling a longer path, arrives now, delivering a message we are finally equipped to receive. These are the missing supernova, stellar deaths that went unrecorded in any historical chronicle, yet whose ghostly signatures are now unmistakably present in our data. By analyzing the light from these delayed signals, astronomers can perform a kind of cosmic autopsy. They can determine the star's original chemical composition, estimate its mass, and classify the type of explosion that tore it apart, all from an event that no human eye ever witnessed directly. This builds a richer, more complete timeline of violent events in our galaxy's life. We are filling in the gaps in our own cosmic history, discovering that the Milky Way has experienced more frequent and more varied stellar cataclysms than our historical records alone would suggest. This archaeological dig extends to the most powerful blasts of all. Some astronomers theorize that certain faint, lingering glows could be the extremely delayed echoes from ancient gamma-ray bursts, the birth cries of black holes from an era when the galaxy was young and chaotic. Each echo stratum we uncover adds another data point, helping us chart the rate of star formation and death over billions of years. This long-term perspective is crucial. It reveals the universe's evolutionary path, showing how the frantic star-making of its youth has gradually settled into the more measured rhythm we see today. And this same archaeological method is now being applied to the more subtle, repeating stories written by the universe's strange variable stars. V838 Monocerotis defied every known category of stellar outburst. It was not a nova, not a supernova, but a colossal stellar sneeze that temporarily made it the brightest star in our entire galaxy. Then, as quickly as it flared, it began to fade. But that was when the real show began. A spectacular light echo emerged, a glowing shell of light that swelled outward like a cosmic smoke ring. This was not a simple ring, however. The echo illuminated a series of intricate, nested dust shells that had been completely invisible before the eruption. The geometry was breathtakingly clear, a fossil record of dust ejected by the star in its turbulent past. The leading explanation for this bizarre event is a stellar merger, a slow, gravitational dance of two stars spiraling inward until they finally embraced, triggering a titanic eruption that ejected their outer layers without completely destroying the system. The light echo acted as a probe, charting the complex architecture of this newly formed object and its immediate surroundings. Luminous blue variables offer another window into stellar oddities. The volatile giant Eta Carinae, a star system so massive it seems to be tearing itself apart, experienced a giant eruption in the 1840s that briefly made it the second brightest star in the night sky. Light echoes from that 19th century event are still arriving today. By analyzing this ancient reflected light, astronomers can study the eruption's precise light curve and spectrum, details lost to time in historical visual records. These echoes show how the star's violent outbursts plow into its own previously ejected material, creating a constantly changing nebula of gas and dust. For every strange star, the echo provides the critical data to understand its internal physics. The way the echo brightens and fades over months or years directly reveals the total energy of the outburst and its exact duration. Was it a single, sharp spike or a series of rolling pulses? This timeline tests theories of stellar instability, helping scientists model the violent processes that drive these stars to the brink. Each unusual echo forces a re-evaluation of our stellar classification system. These are not neat textbook cases. They are the exceptions that prove our rules are incomplete, pushing us to create new models for stellar behavior we are only beginning to comprehend. This entire menagerie of cosmic ghosts, from supernova to stellar mergers, sets the stage for an even more profound discovery. We are now learning to listen for the echoes of events that produce no light at all, only ripples in the fabric of spacetime itself. The fabric of spacetime itself can ripple. When two incredibly dense objects like neutron stars spiral into each other, they do not just flash with light, they shake the universe, sending out waves of gravity that stretch and compress everything in their path. Our first direct confirmation of these gravitational waves opened an entirely new sense with which to perceive the cosmos. But what if we could also see the afterglow of these collisions, long after the initial flash has faded? This is where light echoes enter the multi-messenger era. A neutron star merger often produces a kilonova, a brief, intense flash of light responsible for forging heavy elements. The initial burst of light and gravitational waves arrives at Earth almost simultaneously. Yet, years later, that same flash of light could still be traveling outward, striking a distant dust cloud and reflecting back toward us as a faint, expanding ring. This delayed echo would be a priceless electromagnetic counterpart to the original gravity signal. It would offer a second, completely independent chance to study the cataclysm. By analyzing the echo spectrum, we could directly confirm the creation of specific elements, like gold and platinum, in the violent aftermath. The very presence of these elemental fingerprints in the echo would be definitive proof that these cosmic collisions are the universe's primary forges for the heaviest atoms. The shape of the echo itself would reveal the geometry of the merger. Was the material ejected in a uniform sphere or in focused, lopsided jets? The echo's evolving form would tell us, providing a three-dimensional view of the explosion structure that the initial, fleeting observations might have missed. While no confirmed light echo from a gravitational wave event has been found yet, dedicated searchers are already scanning the skies. The potential is staggering, a perfect synergy between the oldest messenger, light, and the newest, gravity. This integrative approach is the future of astronomy, weaving together different signals to create a single, coherent story of cosmic violence. This quest to see the unseen naturally extends to the universe's most elusive substance. Could these same ghostly reflections offer any clue to the nature of dark matter? Dark matter casts no shadow and emits no light, yet its invisible hand might still leave a mark on these cosmic ghosts. The immense gravity of a dark matter clump hidden within a galaxy could subtly warp the path of a light echo, bending its trajectory like a lens. Detecting this faint distortion is one of astronomy's ultimate challenges, like trying to measure the ripple from a single pebble dropped in a stormy ocean. But the potential reward is profound, a way to sense the unseen scaffolding of the cosmos through its effect on delayed starlight. A more promising path lies in the silent, dark matter-dominated realms of dwarf galaxies. These faint satellite galaxies are overwhelmingly made of dark matter, with very little of the normal stuff we see. When a supernova erupts in one of these dark realms, its light echo does more than replay the explosion. It illuminates the interplay between the dark matter's gravitational pull and the behavior of the scant normal matter, the gas and dust that is there. By studying how these echoes evolve in such extreme environments, we can infer how dark matter governs the motion of gas, influences the birth of stars, and ultimately shapes the entire ecosystem of a galaxy. While a light echo will never show us a dark matter particle directly, it provides critical context. Every echo helps us build a more precise three-dimensional map of the normal matter, the luminous dust and gas. And since normal matter is gravitationally entwined with dark matter, tracing one helps us trace the other. These faint reflections become part of a vast, interconnected puzzle, where understanding the behavior of visible light indirectly tests our models for the invisible universe that holds it all together. This subtle dance between light and shadow, between the seen and the unseen, finds a parallel in the very beginnings of planetary systems, where dust is not a cosmic mirror, but the raw material for new worlds. The dusty cradles of newborn planets hold secrets light echoes are uniquely positioned to reveal. Around a young star, a swirling disk of gas and dust is the construction site for entire worlds, a chaotic nursery where particles collide and coalesce. A sudden stellar outburst, a flare from the infant sun, sends a pulse of light racing through this protoplanetary disk. The resulting echo does not form a simple ring. Instead, it paints a complex picture of the disk's inner geography, highlighting its hills and valleys. A dark gap in the echo's structure is not an empty void. It is a cosmic construction zone, a path cleared by the gravitational pull of a newly formed planet as it sweeps its orbit clean of debris. This is how we can witness planets in the act of being born, not by seeing the planet itself, but by seeing the shadow it casts upon the stellar dust. Young stars like Fu Orionis objects are perfect for this kind of study. These tempestuous suns experience violent accretion bursts, sudden flares of brilliance as massive clumps of material from the disk come crashing down onto their surfaces. Each burst creates its own light echo, a flash that propagates through the surrounding disk. By watching how that echo evolves, astronomers can trace the density and temperature of the disk material, understanding how these violent feeding frenzies deliver the raw ingredients for planet building. The very quality of the reflected light tells a deeper story. As the echo's light scatters off the dust grains in the disk, it carries a signature of their size and composition. Are the particles fine, primitive dust, or have they begun to clump into larger pebbles and rocks, the first step toward forming a planetesimal? The echo can reveal a mix of silicate minerals and carbon-rich ices, the fundamental Lego blocks for terrestrial planets and gas giants alike. This dynamic view helps explain the staggering diversity of exoplanetary systems we have discovered. Why do some stars host tightly packed rocky worlds while others have distant gas giants? The answer lies in the initial conditions of these protoplanetary disks, conditions that light echoes can now probe. By understanding the specific environments that give rise to rocky planets within a star's habitable zone, the region where liquid water could exist, we take a significant step toward answering one of humanity's oldest questions. Are the ingredients for life a rare cosmic accident, or are they a common outcome of the very processes that build worlds? A supernova's echo carries more than just light. It delivers a surge of energy capable of rewriting a planet's biological destiny. The same flash that paints a ghostly ring in our telescopes also unleashes a torrent of radiation and high-energy particles, a cosmic fallout that can travel for light years and bathe entire worlds. By studying the geometry and timing of these echoes, we can work backwards to identify historical supernova events that might have swept past our own solar system. The evidence for these past cosmic irradiations is buried deep within our own planet. In sediment layers on the ocean floor, scientists have found spikes of radioactive iron-60, an isotope that is forged only in supernova explosions. This is a direct fingerprint of nearby stellar cataclysms, events close enough to have showered Earth with their debris. Light echoes provide the crucial context for these discoveries. If we can find an echo from a supernova remnant in our galactic neighborhood, we can calculate its distance and the precise moment its initial flash and particle wind would have reached us. This allows us to match a specific cosmic event to a specific layer in the geological record, connecting a stellar death to a potential turning point in Earth's evolutionary history. Such an event could have delivered a double-edged sword. A nearby supernova's radiation might have stripped away atmospheric layers, damaging the ozone layer and exposing life to harmful ultraviolet rays from our own sun. This could have triggered mass extinctions, clearing the stage for new forms of life to emerge. At the same time, the increased radiation might have accelerated mutation rates, potentially driving evolutionary innovation in unexpected ways. This astrobiological perspective extends far beyond Earth. When we observe a light echo from a star known to host exoplanets, we are seeing a record of the stellar activity that planet has endured. A violent flare or outburst captured in the echo's fading light shows us the kind of radiation bath that could have sterilized a nearby world or sparked complex chemistry in its atmosphere. This helps us assess the true meaning of the habitable zone, that Goldilocks region where water can be liquid. It is not just about distance from the star, but also about the star's stability and its history of cosmic violence. A planet might orbit at the perfect distance, but if its sun is prone to frequent, deadly outbursts, its chances for life are dramatically diminished. Light echoes give us the long-term climate history for other worlds, written in light. This profound link between stellar death and the potential for life shows that our own story is inseparably woven into the explosive cycles of the galaxy. To trace these subtle connections across such vast distances, we have been forced to build ever more sensitive eyes on the sky. The faintest cosmic whispers demand the most advanced ears we can build. Studying light echoes has directly driven the creation of more sensitive detectors and faster data processing systems. To capture these transient, ghostly rings, our instruments must see farther and fainter than ever before. The James Webb Space Telescope represents a quantum leap in this pursuit. Its powerful infrared eyes are perfectly suited for peering into the dusty nurseries where stars are born, and where supernova light often bounces back to us. Infrared light slips through dust that blocks visible light, allowing Webb to see the echoes hidden within cosmic clouds, revealing details we have been blind to for centuries. But a telescope is only as good as the data it can process. The sheer volume of information from observatories is staggering. This is where machine learning enters the stage. We can now train sophisticated algorithms to sift through millions of astronomical images, teaching them to recognize the subtle, expanding pattern of a light echo against a background of stars and noise. This is not a simple task. It is like teaching a computer to spot a single, faint smoke ring drifting across a sky filled with fireworks. Upcoming projects like the Legacy Survey of Space and Time from the Vera C. Rubin Observatory will generate such an immense flood of data that only artificial intelligence can hope to manage it, scanning the entire visible sky every few nights for changes. The hunt for these fleeting phenomena also pushes the development of global telescope networks. When an alert goes out that a potential echo has been spotted, telescopes around the world and in space can swing into action, coordinating observations across different wavelengths to build a complete picture before the echo fades. This relentless drive to capture cosmic ghosts creates a powerful technological synergy. The advanced cameras developed to catch a faint supernova echo are the same ones that can detect the subtle dimming of a star as an exoplanet passes in front of it. The machine learning models trained on echo patterns can be repurposed to find distant galaxies or classify strange stellar behavior. Every time we push the boundaries to study one mystery, we create new tools that unlock a dozen others. This self-reinforcing cycle of discovery and innovation ensures that our quest to understand the past lights of the universe will continue to illuminate its future. The next generation of sky surveys will turn the cosmos into a living movie. The Nancy Grace Roman Space Telescope, set to launch in the next few years, will possess a field of view over 100 times larger than the Hubble Space Telescopes. It will not just take pictures of the sky, it will scan it repeatedly and relentlessly, creating a time-lapse view of the entire visible universe. This relentless gaze is perfectly suited for catching the birth of light echoes. Instead of stumbling upon them by chance, we will watch them emerge, track their growth over years, and catalog them by the thousands. This flood of new data will do more than just add to our collection. It will allow for the first true statistical census of these phenomena. How common are they really? Do certain types of echoes cluster in the spiral arms of our galaxy, where star formation is most active? Are there entire classes of stellar outbursts we have missed because their light only reaches us as a faint, delayed reflection? The Roman telescope will answer these questions, transforming echoes from rare gems into a measurable population. This statistical power will be amplified by a global network of observatories. International collaborations are already planning for a future where an alert from a space telescope triggers an immediate response from a ground-based instrument in Chile, followed by a detailed spectral analysis from a telescope in Hawaii. This coordinated effort will capture the entire life cycle of an echo, from its first faint glimmer to its final dissipation. Further into the future, space-based interferometers could combine the light from multiple telescopes flying in precise formation. This would give us an unimaginably sharp view, allowing us to resolve fine details within a single echo, perhaps even seeing the intricate structures within the reflecting dust clouds themselves. With these tools, light echoes will cease to be mere curiosities. They will become routine, reliable instruments in the astronomer's toolkit, as standard as a thermometer or a spectrograph. This coming flood of precise data, however, is set to challenge the very models we use to explain the universe's most violent events. These cosmic ghosts are not just messengers, they are interrogators. The data they bring often clashes with our best simulations, forcing a complete rethinking of the fundamental physics governing stellar deaths. For instance, some supernova echoes arrive far brighter than our models predict. This excess light implies an explosion of staggering, almost impossible energy, a power source that our current theories for how stars die simply cannot account for. It forces physicists back to their blackboards, sketching out wild new possibilities like magnetars with unimaginably powerful magnetic fields or failed supernova that collapse directly into black holes. processes that could unlock reservoirs of energy we have never before considered. Another persistent puzzle lies in the dust itself. According to conventional wisdom, the blistering shockwave from a supernova should vaporize every dust grain in its path, scouring space clean for light years. Yet light echoes frequently gleam from regions directly behind these very shock fronts. The dust is clearly still there, shining back at us. This paradox suggests that dust can reform with incredible speed in the turbulent, expanding wreckage, condensing like soot in a cooling fireball faster than anyone thought possible. These discrepancies are not failures, they are the engine of scientific progress. Each anomalous echo, each piece of data that refuses to fit, acts as a cosmic wrench thrown into the gears of our theoretical machinery. To make the models work, astrophysicists must refine their simulations of extreme fluid dynamics, the behavior of matter under conditions we can never replicate on Earth. They have to improve how they track the transfer of radiation through expanding debris and recalculate how shock waves accelerate particles to nearly the speed of light. This iterative process, this constant conversation between prediction and observation, is how our understanding of the universe genuinely evolves. Every mysterious echo is an open question written across the sky, a direct challenge to our intellect that pushes the very boundaries of knowledge. And as we wrestle with these profound scientific questions, it is worth remembering that these celestial phantoms have also captured something deep within the human spirit, inspiring art and stories long before we knew their true nature. Long after the equations are written, these celestial ghosts linger in the human imagination. A light echo is more than a physical phenomenon. It is a powerful symbol that the past is never truly silent. Artists have painted their expanding rings as luminous halos in the cosmic dark, while poets have used them as metaphors for memory, for how a single moment of beauty or trauma can reverberate through a lifetime, its reflection returning to us when we least expect it. In music, composers have tried to capture their ethereal quality, translating the slow, silent expansion of light into soundscapes that feel both ancient and new. This cultural resonance touches something deep within us, a universal recognition that we, too, are surrounded by the echoes of our own history. Philosophically, these echoes dissolve the hard line between past and present. They provide a tangible, observable example of how an event that concluded centuries ago can still communicate with us directly, its energy and information arriving now, as fresh as the day it was born. This challenges our everyday experience of time as a strict, linear progression. It suggests the universe operates with a kind of temporal depth, where moments are not simply erased but continue to exist, their light still traveling, still capable of illuminating the present. In classrooms and planetariums, this makes the mind-bending concept of light-speed delay instantly graspable. It is one thing to be told that we see the stars as they were. It is another to watch a ghostly ring swell year by year, proving that delay in a visceral, unforgettable way. Public captivation with events like the V838 Monocerotis echo transformed abstract astronomy into a shared human experience. Its beautiful, smoke ring images circulated across the globe, not just in science journals, but in news reports and social media feeds, inviting everyone to witness a cosmic mystery unfold. This fusion of science and culture enriches our pursuit of knowledge, reminding us that the desire to understand the stars is inextricably linked to our need for meaning, beauty, and connection. And in this grand, collaborative endeavor, some of the most watchful eyes belong not to giant institutions, but to dedicated individuals gazing at the sky from their own backyards. A brilliant flash in the cosmos does not always need a billion-dollar telescope to be seen. Some of the most dedicated watchers of these cosmic ghosts are amateur astronomers, whose passion and persistence have rewritten entire chapters of the story. When the star V838 Monocerotis erupted, professional observatories captured stunning images, but they could not watch it continuously. It was the global network of amateur astronomers with their own backyard telescopes and digital cameras who tracked the echo's expansion night after night. They filled in the crucial gaps between professional observing runs, documenting its subtle changes in brightness and shape with a level of detail that would have otherwise been lost. This was not a one-time event. Online platforms now connect these passionate observers directly with research institutions, creating a powerful citizen science engine. Amateurs routinely scan wide swaths of the sky that might be between the crosshairs of more focused professional surveys, and their sharp eyes often catch the first flicker of a new transient event, a potential new light echo being born. This democratization of astronomy means a discovery is no longer confined to the mountaintop observatory. It can happen in a suburban garden with findings uploaded to a collaborative database in minutes. That persistent monitoring, watching the same patch of sky for years, requires a special kind of dedication that complements the scheduled time on large telescopes. This collaborative spirit, where a hobbyist's keen observation can contribute to a scientific paper, makes the entire field richer and more dynamic. It proves that the universe's grandest mysteries can be unlocked not just by a few, but by anyone with curiosity and a willingness to look up. This same spirit of making cosmic wonders accessible is now transforming how we teach the next generation of explorers. That faint ring of light is a perfect classroom for the cosmos. To grasp this grand phenomenon, you can start with a simple experiment right at home. Shine a flashlight into a dark, dusty room. You will not just see the beam itself, you will see the cloud of dust particles illuminated in its path. If you flash the light briefly against a distant wall, you might even see a faint, lingering glow from the dust motes, a miniature echo of the original burst. This is the fundamental principle at play, scaled down to human dimensions. In the classroom, interactive simulations take this further. Students can adjust virtual sliders to change the distance to a cosmic dust cloud, or even tweak the speed of light itself, watching in real time as their changes warp the size and timing of the resulting light echo rings on their screens. This hands-on manipulation transforms abstract equations into an intuitive understanding of geometry and timing. The learning deepens with access to real scientific archives. Imagine a student project where a class downloads actual images of a supernova remnant taken by the Hubble Space Telescope over a decade. By comparing these images year by year, they can measure the expansion of a real light echo, calculating its growth rate and using that to estimate the distance to the star. This is not a hypothetical exercise, it is authentic data analysis, giving young minds a true taste of the scientific process. Educators use these tools to bridge the vast gap between a textbook diagram and the dynamic reality of the universe. A lesson on the finite speed of light becomes unforgettable when you can watch its delayed consequences unfold across years of telescopic observations. This sparks a deeper curiosity, not just about the event itself, but about how we know what we know. The story of a light echo is a story of forensic science on a cosmic scale, teaching the next generation how to interrogate the light from the sky. This powerful educational role, inspiring future astronomers and engineers, is a profound justification for the resources required to study them. The price of peering into the cosmic past is measured in more than just time. Every stunning image of a ghostly ring of light represents a substantial investment in engineering, computing, and human intellect. Building and launching space telescopes like Hubble and James Webb costs billions of dollars, while the supercomputers that process their data and the global networks that store it require constant funding and maintenance. This is the economic reality of fundamental science, a long-term investment with no guaranteed immediate return. Yet this investment ignites a powerful engine of innovation. The challenge of detecting the faintest possible light echoes has driven the development of exquisitely sensitive camera sensors. These same detectors, originally designed for deep space observation, are now found in medical imaging devices, allowing doctors to see inside the human body with unprecedented clarity for earlier disease detection. The sophisticated algorithms created to sift cosmic signals from noise are now used to improve security scanning, financial modeling, and even the accuracy of weather prediction. This technological spin-off is a silent, continuous dividend paid by our curiosity about the stars. Beyond technology, the pursuit of these cosmic ghosts creates a vibrant ecosystem of high-skilled jobs. Engineers, software developers, technicians, and project managers are all employed in the design, construction, and operation of these grand observatories. Major astronomy projects are rarely the work of a single nation. They are monumental exercises in international cooperation, forging partnerships between countries that might otherwise have little common ground, united by a shared goal of understanding the universe. The cost of a single space mission is indeed vast, but its value must be weighed against its scientific yield and its power to inspire generations. The breathtaking images and profound discoveries that result capture the public imagination, fostering a culture that values knowledge and education. This cultural shift can, in turn, influence government policy and increase support for science funding and STEM education, creating a virtuous cycle of investment and discovery. While society's resources are always finite, the returns from fundamental research are profound and multifaceted. It is not merely about what we learn about distant supernova, but about what we learn about ourselves and our capacity to achieve the remarkable. This practical necessity of managing such powerful tools and profound knowledge brings with it a crucial set of responsibilities. Our ability to listen to the echoes of the cosmos comes with a deep responsibility. The vast telescopes built for this purpose are almost always funded by public money, raised from taxpayers around the world. This creates a fundamental ethical duty to ensure that the precious data they collect is not locked away in private archives but is shared openly and freely with the global research community. When data from a mission like the Hubble Space Telescope is made accessible to any scientist, regardless of their institution or nationality, it fosters a spirit of collaboration that accelerates discovery. A researcher in a developing nation can analyze the same light echo as a team at a prestigious university, bringing a fresh perspective that might crack a puzzle others missed. This equity is the bedrock of modern science, transforming individual observation into a collective human endeavor. Yet this grand pursuit casts a shadow, literally. The immense, piercing beams from giant ground-based observatories can spill beyond their mountaintops, washing out the pristine darkness of the night sky. This light pollution does not just hinder astronomy, it disrupts the natural rhythms of local wildlife and can infringe upon the cultural heritage of communities who have lived under these stars for generations. The question becomes how to balance our quest to understand the universe with our duty to preserve the local environment and respect the people who call these places home. Broader debates also simmer over funding priorities. Is it right to allocate hundreds of millions of dollars to study stellar ghosts when that same money could address pressing social needs on Earth? There is no simple answer, but history shows that the technological and intellectual spin-offs from fundamental research often yield unexpected and profound benefits for society. from medical imaging to the very internet that connects us. Furthermore, ethical science demands that we listen as well as look. In some cultures, the patterns in the sky are part of a living narrative, an indigenous knowledge system passed down through millennia. Respecting this wisdom and considering it alongside our data is not just an ethical imperative. It can offer unique insights that pure data analysis might overlook. These considerations ground our cosmic ambitions, reminding us that every observation is made from a fragile world with its own complex needs. This connection between the stars and our planet extends even to the very air we breathe, where the same principles that illuminate stellar cataclysms can help us understand the delicate balance of our own climate. The same principles that paint ghostly rings in deep space also govern the delicate balance of our own world. A supernova's light echo is a delayed message, and Earth's climate system operates on a similar principle of lag and reflection. A massive volcanic eruption, for instance, can blast sunlight reflecting aerosols high into the stratosphere, causing a temporary global cooling. But the full effect is not immediate. It ripples through the atmosphere for years, a climatic echo of that single violent event. The way we model how light propagates through cosmic dust, scattering and reflecting over vast distances, directly inspires how we simulate the complex journey of solar energy through our own atmosphere and oceans. These are not separate sciences, they are different expressions of the same physical laws. Consider the powerful climate feedback loops that worry scientists today. The ice albedo effect is a perfect terrestrial parallel. As polar ice melts due to warming, it reveals darker ocean or land beneath, which absorbs more solar heat instead of reflecting it, which in turn leads to more melting and more warming. This is a delayed, self-reinforcing cycle, much like a light echo growing brighter as it illuminates more dust. The mathematical tools used to understand one can be adapted to unravel the other, creating a powerful cross-disciplinary conversation. This unity of principle extends to our methods of observation. The sophisticated remote sensing techniques developed for astronomy, analyzing the faint light from distant nebulae, are the very same ones used by climate satellites to measure global sea surface temperatures, track atmospheric carbon dioxide, and monitor the health of polar ice sheets from orbit. We are using the universe as a laboratory to better understand our own planet. This perspective enriches both fields, showing that the cosmos is not merely a collection of distant wonders, but a source of profound insight into the systems that sustain life right here at home. By drawing these deep connections between the celestial and the terrestrial, we empower new generations to explore these mysteries for themselves, often through the immersive lens of digital worlds. These ghostly rings of light are now stepping out of scientific papers and into our hands. Virtual reality experiences are transforming these cosmic phenomena into something you can not just see but inhabit. Picture putting on a headset and finding yourself floating in the void at the very center of a supernova remnant. A shimmering, expanding shell of light, reconstructed from real telescope data, grows around you, its delicate structures close enough to touch. This is not science fiction. Museums and planetariums are creating these breathtaking walk-through simulations, turning abstract concepts into visceral, unforgettable journeys. You can watch a replay of a stellar explosion from multiple angles, or follow a single photon on its centuries-long journey to a dust cloud and back. The sheer scale and beauty of the event becomes intuitively understood, not just intellectually noted. The engagement continues online, where interactive models let anyone play cosmic scientist. You can adjust the distance to a dust cloud, change the power of the original flash, and instantly see how those changes warp the resulting echo. What happens if the star exploded asymmetrically? The ring distorts into a broken, lopsided shape right before your eyes. This hands-on experimentation demystifies the underlying physics, making complex geometry and light travel time feel as natural as a video game. For researchers, this technology is more than a teaching tool. It is a new analytical instrument. They can don their own VR gear and step inside a three-dimensional map of an echo's structure, spotting subtle density variations and magnetic field alignments that might be missed on a flat screen. This immersive data visualization helps them perceive patterns and relationships within the multi-dimensional information, turning numbers into a navigable landscape. By making the science this accessible and visually compelling, we build a bridge between the research community and the public. A person who has virtually stood inside a light echo is far more likely to feel a personal connection to the cosmos, fostering a deeper scientific literacy and a sense of shared wonder. This powerful blend of education and advanced technology ensures that the story of these cosmic ghosts reaches everyone. Yet for all the power of these new tools, our view of the echoes remains frustratingly incomplete. Even our most powerful tools have blind spots. Light echoes are no exception, offering a ghostly glimpse of the past that is often faint, fragmented, and open to interpretation. Their greatest strength is also a primary limitation. They depend entirely on the chance alignment of cosmic dust. A supernova might be the most brilliant explosion in the galaxy, but if its light expands into an empty void with no dust clouds to act as mirrors, it will leave no echo for us to find. We only see the reflections from clouds positioned in just the right place, at just the right distance. This selective vision means our map of past stellar cataclysms is inherently incomplete, biased toward events that happen to have reflective surfaces in their vicinity. When we do capture an echo, the measurements are filled with uncertainty. Calculating the distance to the original event requires knowing the precise geometry of the dust cloud, a shape we often have to infer from the echo itself. If our model of the cloud is slightly wrong, our distance calculation can be off by light years. The properties of the dust itself add another layer of complexity. How reflective are its grains? Are they large or small? These factors change how the light scatters and dims, injecting potential error into our analysis of the original flash's true brightness and energy. Perhaps the most subtle challenge is distinguishing a true light echo from other cosmic mirages. A faint, circular nebula might be mistaken for an echo, or the glowing shockwave from a more recent, unrelated event could create a similar signature. Astronomers must be cosmic detectives, ruling out these other possibilities before they can trust the echo's story. These limitations do not diminish the value of light echoes, they simply define their role. They are a complementary tool, one piece of a larger puzzle. Their data becomes most powerful when combined with other observations, like direct images of the supernova remnant or gravitational wave detections. This multi-pronged approach cross-checks results and builds a more reliable, three-dimensional understanding. Acknowledging these challenges is not a sign of weakness, but a commitment to robust science. It forces careful interpretation and fuels the drive for better technology. Future telescopes with superior sensitivity will detect fainter echoes, while advanced computer models will simulate dust clouds with greater accuracy, steadily whittling away at these uncertainties. Yet some inherent ambiguities will always remain, a humble reminder that we are deciphering messages from a vast and complex universe. This honest assessment of what we can and cannot know prepares us for an even more profound question. Could these same faint reflections ever carry a message that was deliberately sent? The same faint reflections that replay stellar deaths could theoretically carry a message. What if an advanced civilization seeking to announce its existence across the galaxy did not broadcast a simple radio signal, but engineered one designed to echo. They might aim a powerful burst of light or energy at a known, vast dust cloud, calculating the precise geometry so that the reflected signal would sweep across hundreds of star systems like a lighthouse beam, repeating its passage for centuries. This is a speculative, almost poetic idea within the search for extraterrestrial intelligence, yet it underscores the creative thinking that defines the field. While no such engineered echo has ever been found, the concept stretches our imagination about how a civilization might use the universe's own structures to communicate. More practically, the natural echoes we do observe serve as critical environmental reports for potential life. When we see a light echo from a historical supernova, we are seeing a record of the radiation that flooded a particular region of space. If that region contains an exoplanet, the echo tells us that world was once bathed in a wave of high-energy particles. This information helps us assess its astrobiological potential, revealing whether it endured a sterilizing event or perhaps a surge of radiation that drove rapid mutation. SETI researchers already consider how transient cosmic events like supernova could be used as natural synchronization points or powerful beacons for interstellar messaging. Light echoes add a profound temporal dimension to this idea, suggesting that a message might not arrive just once, but could be deliberately rebroadcast by the cosmos itself, long after the original senders are gone. This connection, while distant, exemplifies how the tools developed to understand fundamental astronomy can inspire the broadest and most profound searches of all. It challenges us to look at every flicker in the sky not just as a physical phenomenon, but as a potential carrier of meaning. And as we ponder the possibilities of intelligence and life, we are inevitably drawn to the ultimate scale, using these same echoes to trace the destiny of the entire cosmos. The faint rings of light we observe are more than just delayed messages. They are pages in the universe's own history book. Each echo captured from a different era provides a unique snapshot, allowing us to assemble a timeline of cosmic evolution. By comparing echoes from recent supernova with those from older, more distant events, astronomers can trace profound changes over billions of years. They see how the early universe, rich with massive, short-lived stars, produced frequent, violent explosions that seeded space with the first heavy elements. As the cosmos aged, the stellar population changed, and the rate of these cataclysms slowed, altering the very chemistry of galaxies. This historical record is crucial for modeling the universe's ultimate fate. Will it continue expanding forever, cooling into a silent heat death, or could another destiny await? The data gleaned from these light echoes, detailing how matter and energy have interacted across time, feeds directly into our simulations of these grand scenarios. The most elusive echoes would be those from the primordial universe, the faint, redshifted ghosts from the first stars and galaxies. If we could ever detect them, their light would have been stretched on its immense journey, transformed into long, weak radio waves. Yet within that whisper would be a direct glimpse of the cosmic dawn, a record of the conditions that set everything in motion. This vast perspective, built from countless delayed flashes, places our human timeline in a humbling context. Our entire recorded history is but a single, brief flicker in an epic narrative of cosmic transformation. The drive to understand this evolution is a central pillar of astronomy, and each light echo we decipher adds another crucial piece to the puzzle. As we peer further back in time, we are also forced to look forward, to consider not only the fate of the cosmos but the personal meaning we find in our own fleeting, yet deeply connected, place within its story. That shimmering ring on a telescope screen is more than data, it is a bridge across centuries. To witness a light echo is to feel the fabric of time itself, a direct connection to a stellar cataclysm that unfolded long before our modern world existed. Many astronomers speak of a quiet humility when tracking an echo's slow expansion, a moment where they are not just observers but true time travelers, receiving a message sent on a detour through the cosmos. This profound sense of awe is often the spark that ignites a lifelong passion, turning a casual curiosity into a driving force for exploration. It influences a student's decision to study physics, an artist's choice to paint the cosmos, or a writer's quest to tell stories of deep space. Science, at its heart, is a deeply human endeavor. Behind every major discovery are personal stories of late nights at the observatory, the shared excitement of a team seeing a new ring materialize for the first time, and the collective frustration and triumph that define the search for understanding. These human moments, the camaraderie and the wonder, are the soul of the scientific journey, reminding us that we are not separate from the universe we study, but an active, conscious part of its ongoing story. This reflective connection to the cosmos naturally finds its way into the stories we tell each other, transforming complex data into shared cultural touchstones. The breathtaking echo from V838 Monocerotis did more than captivate astronomers. It became a global media star. Its image, a perfect cosmic smoke ring, graced news broadcasts and magazine covers, transforming an abstract astrophysical concept into a shared moment of public wonder. Science fiction has long embraced this imagery, portraying light echoes as shimmering gateways to the past or as the lingering signatures of ancient alien beacons. While a dramatic leap, these fictional explorations tap into a genuine human fascination with time and memory, using the echo as a powerful metaphor for how the past constantly touches the present. Documentaries walk a finer line, striving to balance scientific accuracy with visual spectacle to make the invisible forces of the cosmos comprehensible and thrilling. When a show like Cosmos dedicates time to explaining the phenomenon, it does more than inform, it inspires. A child who sees that glowing ring on screen might be sparked with a curiosity that leads them to a career in science or engineering. This cultural footprint creates a vital feedback loop. Public fascination, fueled by compelling media, generates support for the telescopes and space missions that make the next discovery possible. It shapes our collective vision of the universe, not as a cold, empty void, but as a place of profound beauty and dynamic history. The stories we tell about these cosmic ghosts inevitably evolve with our technology, from printed illustrations to immersive virtual reality experiences. Yet at their core, they all reflect a fundamental desire to find narrative and meaning in the light from the sky. This deep cultural resonance demonstrates that understanding the universe is not a task for astronomers alone, but a collaborative endeavor that draws from every facet of human creativity. A single light echo connects worlds of knowledge far beyond astronomy. The faint light bouncing off a cosmic dust cloud is a message that physicists, chemists, and geologists can all read in their own language. For a physicist, that echo is a pristine laboratory for studying the fundamental dance between light and matter, governed by the elegant rules of quantum electrodynamics. They can calculate the precise angle a photon will scatter when it strikes a microscopic dust grain, a fundamental interaction that scales up to create the shimmering ring we see in a telescope. Chemists, meanwhile, dissect the echo's spectrum like a cosmic forensics report. The dark absorption lines in its rainbow of colors reveal the exact minerals present in that distant dust cloud, identifying silicates, graphite, and even frozen water molecules. Geologists then compare these extraterrestrial mineral signatures to samples found on Earth, from volcanic ash to meteorites, searching for common threads in the universal recipe for rocky matter. This interdisciplinary conversation solves problems that would stump any single field. To truly understand why a dust grain forms with a specific crystalline structure in the harsh environment of space requires a hybrid expertise, a blend of astrophysics and material science. This collaborative spirit extends to the digital realm, where computer scientists design sophisticated machine learning algorithms to find these faint echoes in a sea of telescopic data, while artists and animators transform the raw numbers into breathtaking visualizations that allow us all to witness the cosmic drama. This synergy is the new frontier of discovery, where the most profound mysteries are solved not in isolated labs, but at the vibrant intersections between traditional fields of study. Our journey through these cosmic whispers reveals a universe that is anything but silent. Light echoes are far more than beautiful apparitions. They are fundamental tools for cosmic time travel. They grant us the impossible power to witness the universe's most violent events long after the initial flash has faded, turning supernova and black hole eruptions into repeatable experiments. Each faint ring is a precise instrument, a celestial tape measure that helps us map the vast distances between stars and galaxies with newfound accuracy. These ghosts illuminate the invisible architecture of space itself, charting the distribution and composition of the dark dust clouds that drift between the stars, clouds that are the very raw material for new worlds. The data they provide acts as a relentless interrogator, constantly testing and refining our best astrophysical models of stellar death and rebirth. The pursuit of these faint signals has directly driven technological marvels, from the exquisite cameras of space telescopes to the sophisticated algorithms that sift meaning from cosmic noise. Culturally, they resonate as powerful symbols of memory and connection, inspiring art and philosophy while reminding us of our humble place in a vast, evolving cosmos. The stories they tell are epic narratives of violence and beauty, connecting the death of a single star to the large-scale processes that shape entire galaxies and seed the universe with the elements essential for life. The enduring mysteries they help us unravel, from the nature of dark matter to the origins of planets, underscore that cosmic inquiry is a dynamic, ever-advancing frontier. Every new echo we discover holds the potential for a surprise, a piece of data that does not fit, forcing us to rethink our understanding and driving science forward into uncharted territory. This is not the end of the story, but a new beginning. As our tools grow ever more sensitive and our surveys ever wider, we stand on the threshold of a new era, ready to listen as the universe reveals its next chapter, written in light. The universe is not a silent archive, but a living chronicle speaking to us through these shimmering ghosts of light. Our journey has taken us from the fundamental physics of a single photon, scattering off a dust grain, to the profound philosophical realization that the past is never truly lost. These echoes are more than scientific tools. They are bridges across time and space, allowing us to witness the death cries of stars and the feeding frenzies of black holes as if they were happening now. With every technological leap, our vision sharpens. New telescopes and advanced algorithms will soon reveal thousands more of these cosmic phantoms, each one adding a crucial piece to the grand puzzle of our cosmic origins and destiny. Let this knowledge inspire you to gaze at the night sky with fresh eyes. Understand that the light from every star you see may not be a single message, but a story with multiple chapters, its echoes still traveling through the dark, waiting for the right moment to shine. We would love to hear which of these enigmatic signals captured your imagination the most. Share your thoughts in the comments below. And if you want to continue unraveling the mysteries of the cosmos, subscribe to join us on our next adventure. Together, we follow the trail of light across the ages, forever curious and forever amazed by the story